Hi there, and welcome back to MA211. This is an exciting video because all this work we've been doing developing properties of the Laplace transform, that's finally going to come to fruition when we use the Laplace transform to solve differential equations. So you've seen a few examples of this in the book already, and let's dig right in. First, I want to solve this initial value problem, 2y prime minus y equals 1, and I want y at 0 to be 0. So the first thing I want to do is Laplace transform both sides of the differential equation and express everything in terms of the Laplace transform of y. So what would we have? We'll have, if I Laplace transform this side, let's get a pen going here, I'd have 2 times the Laplace transform of y prime. We write that as 2, that's the S times the Laplace transform of y. I'm going to use the symbol capital Y for that, minus little y at 0. Alright? Minus, so that thing, the Laplace transform of y prime is sitting right here, minus the Laplace transform of y, I'm using the symbol capital Y for that, equals the Laplace transform of the function 1 is 1 over s. So I Laplace transformed both sides. Now I want to use my initial condition and plug it in right here. So what would I have? I'll have 2 times sy minus 0 minus capital Y equals 1 over s. So 2sy minus capital Y equals 1 over s. Now remember, we're looking for the function little y. What I'm going to do is I'll find an expression for big Y. Big Y is the Laplace transform of little y. So I'll figure out what the Laplace transform of little y is, and then I'll inverse Laplace transform that to get little y. So first let's solve for capital Y. Capital Y times 2s minus 1 is 1 over s. Capital Y is 1 over s times 2s minus 1. So now I need to say, well, this is my big Y. Since little y, that's the inverse Laplace transform of capital Y. Let's see, so that's the inverse Laplace transform of 1 over s times 2s minus 1. So what I really need to do is calculate the inverse Laplace transform of 1 over s times 2s minus 1. And we've practiced this before. With this kind of thing, I want to calculate, first I'll calculate the partial fractions decomposition of 1 over s times 2s minus 1, and if you check, that is 1 over s minus 1 half minus 1 over s. And now I can go ahead and inverse Laplace transform with no problem. The inverse Laplace transform here will be e to the 1 half t minus 1. And that's the solution to our initial value problem. Now you could have solved this initial value problem using other techniques. This one's first order linear. You could use an integrating factor to solve this, and you'd get the exact same answer. You should maybe check that to make sure it works out. So let's try another problem. Same thing here. I'll Laplace transform both sides of the ODE. What will I get? I'll Laplace transform the y prime, and I'll get sy minus little y at 0 minus the Laplace transform of y is sitting right here, that's capital Y, equals the Laplace transform of 2 times cosine 5t is 2s over s squared plus 25. That's an s, that's a 5, sorry, my s's and 5's look the same. I'll take my 2, I'll use it as an initial condition, that's sy minus 2 minus y equals 2s over s squared plus 25. I'll solve for capital Y, so I'll factor the left hand side and I'll have y times s minus 1 equals 2s over s squared plus 25 plus 2, so this thing had to come over there. And I'll divide. Capital Y is 2s over s squared plus 25 times s minus 1 plus 2 over s minus 1. And again, now I need to inverse Laplace transform everything. Let's see. In order to do the inverse Laplace transform, I'm going to need the partial fractions decomposition of this thing. This one is easy enough to inverse Laplace transform. There's no problem there. So if I'm careful about it, I can calculate the inverse or the partial fractions decomposition of everything, and I'll get this. This one's a little messy. This is 27 over 13 times 1 over s minus 1 minus 1 over 13 times s over s squared plus 25 plus 5 over 13 times 5 over s squared plus 25. And now we need to inverse Laplace transform everything. Well, that's easy enough. I've written everything in a nice form. Little y of t is the inverse Laplace transform of this part is going to be 27 over 13 e to the t. The inverse Laplace transform of this part will give me minus 1 over 13 cosine 5t. The inverse Laplace transform of this part will give me plus 5 over 13 sine of 5t. Okay, so you should be starting to see a pattern here. You Laplace transform everything, solve for capital Y, inverse Laplace transform everything. Let's try another example here. Once again, I'll Laplace transform everything. We have a y double prime here, so we'll have to pay attention. How do we Laplace transform y double prime? It's s squared capital Y minus sy at 0 minus y prime at 0 minus 4. Laplace transform of y prime is sitting right here. This is sy minus y at 0. Okay, be careful. It's 4 times the Laplace transform of y prime. I see people all the time will write 4 times sy and then minus y at 0, and they'll forget to multiply the y at 0 by 4. So don't do that. And let me see, on the right hand side this will be 6 over s minus 3 minus 3 over s plus 1. I'll use my initial conditions. Let's see, right here and right here and right here. I get s squared y minus s minus 4sy. Let's see, plus 4 is 6 over s minus 3 minus 3 over s plus 1. So let's simplify. Let's solve for capital Y. I'll have y times s squared minus 4s is equal to 6 over s minus 3 minus 3 over s plus 1 plus s minus 4. Divide everything off. I'll just leave it like this, and I'll write it as 6 over s minus 3 minus 3 over s plus 1 plus s minus 4, whole thing divided by s squared minus 4s. Okay, you can type this thing into Maple and ask for a partial fractions decomposition. It'll give it to you. Alright? If you check the partial fractions decomposition, again this is sort of messy, but that's okay. It's 27 over 20 times 1 over s minus 4 plus 9 over 4 times 1 over s minus 3 over 5 times 1 over s plus 1, and then you'll have a minus 2 over s minus 3. You should check and make sure that's what you really get. Again, that just comes from the partial fractions decomposition of this thing. So now I'm in the business of inverse Laplace transforming. Little y of t, it's easy to read off. That first term will give me a 27 over 20 times e to the 4t plus 9 over 4. The next term will give me a 9 over 4 times 1 minus 3 over 5 times the inverse Laplace transform of s plus 1 is e to the negative t, minus 2 times the inverse Laplace transform of s minus 3 is e to the 3t. And that's it. Okay, we'll try another one here. Again, I'll Laplace transform everything. This part gives me s squared y minus sy at 0 minus y prime at 0 plus 9. Laplace transform of y is just capital Y equals, this is 1 over s minus 1. I'll use my initial conditions. They're easy. So I'm left with s squared y plus 9y equals 1 over s minus 1. I'll factor the left-hand side. Y times s squared plus 9 equals 1 over s minus 1. And so capital Y is 1 over s minus 1 times s squared plus 9. If I calculate the partial fractions decomposition of this one, I get the following. This is 1/10 times 1 over s minus 1 minus 1/10 times s over s squared plus 9 minus 1 over 30 times 3 over s squared plus 9. Now I need to inverse Laplace transform, and it's easy. So y of t is 1/10 e to the t, that's the first term, minus 1/10 cosine 3t is the next term, and minus 1 over 30 sine 3t is the last term. Okay, and we'll do one last one here. This one is a higher order ODE, but it's just like everything else. First we'll Laplace transform everything. When I Laplace transform the y triple prime, I'll get an s cubed y minus s squared y at 0 minus sy prime at 0 minus y double prime at 0 plus 2. Again, don't forget it's 2 parentheses Laplace transform of y double prime is s squared y minus sy at 0 minus y prime at 0 minus Laplace transform of y prime is sy minus y at 0 minus 2 capital Y. That's equal to Laplace transform of sine 3t is 3 over s squared plus 9. Now I'll use my initial values and things simplify a lot. I get an s cubed y. Oops, this is supposed to be equals negative 1 there. So then I'll have a plus 1. This one's gone, that one's gone. This one turns into a plus 1. Plus 2s squared y. That thing's gone and that thing's gone. Minus sy. And that one's gone. Minus 2y equals 3 over s squared plus 9. Okay, we'll factor everything out. We'll get y times s cubed plus 2s squared minus s minus 2 equals 3 over s squared plus 9 plus 1. Alright, so capital Y is 3 over s squared plus 9 times s cubed plus 2s squared minus s minus 2 plus 1 over s cubed plus 2s squared minus s minus 2. I want to compute the partial fractions decomposition of this. Again, I just used maple. This one's sort of a bear. You get negative 10 over 39 times 1 over s plus 2 minus 7 over 60 times 1 over s minus 1 plus 7 over 20 times 1 over s plus 1 plus 1 over 130 times 3s minus 6 over s squared plus 9. Okay, and you'll notice there's just a little bit of work left to do. I can inverse Laplace transform this no problem, and that one no problem, and that one no problem, but this one I need to break into two parts before I can inverse Laplace transform things. So let's see, what do I get? Little y is negative 10 over 39 e to the negative 2t from that term minus 7 over 60 e to the t from that term plus 7 over 20 e to the negative t from that term plus 1 over 130. What do I need? I need the inverse Laplace transform of 3s over s squared plus 9, and I have minus the inverse Laplace transform of 6 over s squared plus 9. So that's easy enough. I'm just going to copy down. All of this part is the same. It goes here. This is plus 1 over 130 times the inverse Laplace transform here will be 3 times the cosine of 3t minus, what do we have here? I want a 3 there, so this is 2 sines of 3t. So overall we get negative 10 over 39 e to the minus 2t minus 7 over 60 e to the t plus 7 over 20 e to the negative t plus 1 over 1, let's call that 3 over 130 cosine 3t minus 2 over 130 sine 3t. And that's it. So those are some examples of solving initial value problems using the method of Laplace transform. Once you do several of these, it'll become pretty second nature. Many of you will sort of go to this as your go-to method of solving ODEs, because using the method of Laplace transform, you don't need to worry about what order is it homogeneous or inhomogeneous. It doesn't matter. You do the same thing every time. Basically, as long as it's a constant coefficient ODE, the method of Laplace transform is going to work for you.